good news is I made it here. The bad news is my slideshow didn't. It's on the chip in my pocket, but it won't. It's not recognizable. So it's going to be sort of an ad lib. But I came here with the understanding that I was going to be answering questions about your personal properties and whether there's going to be some particular issue about, given where you're located, what kind of hazards you may be confronted with. But I thought, in the absence of the slideshow, I would tell you first, I thought maybe we'd go over the geology of the Manzanita area first.
If you give me your chip, Tom, I'll see if I can read it.
Oh. Look for Manzanita geohazards, I think I see.
Or your bank account information.
Yeah, since that's about this big, you don't have to worry. One of the things about Manzanita is the mouth of the Nehalem, and this is beautiful scenery you've got here. A lot of people call your hills the Nehalem Alps. I like to call them the Himalayas. If you can pronounce that, you get 5 cents. The reason you have such steep mountains around here is that you are located here at the site of the Miocene Columbia River estuary. The Columbia used to drain right out through the Manzanita area, and we're in the submarine canyon of the Columbia River, which in the good old days, back 15 million years ago, the Columbia entered the Pacific Ocean over where Napa is, near the northeast corner of Clatsop County. When the hot spot that's under the Yellowstone National Park was underneath the Owyhee Mountains and Hills Canyon, it let loose a huge number of extremely large lava flows that are very similar in composition to the lavas that are erupting right now out of Kilauea in Hawaii. Very runny, very black, and they came out in such huge volumes we've called them flood basalts. And the Columbia River flood basalts, one individual flow could come out in a period of less than a month and cover 65,000 square miles of countryside. So it covered western Idaho, much of eastern Oregon and eastern Washington, and it would come down through the Cascades following the Columbia River, which its canyon has moved around as it's been filled by these lava flows, such that at times the gorge was where Mount Hood is, and at other times it's been pushed to the north where it is now. And it came out and spread out into what we now call the Willamette Valley, but what used to be the coastal plain of Oregon. At that time, the Coast Range was just starting to rise out of the ocean. There were just low hills, and rivers like those that drain, heck of a time to dry up on names of rivers, but the Sandy Am, for example, the Clackamas, those didn't drain into the Columbia as we know it now. They drained out to the west. And so as the lavas spread down the coastal plain, they got into these rivers and they flowed out to the ocean. So when the Clackamas was draining, it drained west, and the lavas flowed and built out a lava delta at Tillamook at Cape Meares, for example. If you went back from Cape Meares to the east, you'd go up the Trask River, and at the summit of the Coast Range, here's the Tualatin River going in the other direction. And since the lavas flowed, the Coast Range rose faster than the rivers could cut down, and so it broke and went back the other way, and eventually pooled up with other rivers doing the same thing, turned north, making the Willamette, and it joined the Columbia River. So these lava flows got in before the Willamette River existed, and accounts for Yaquina Head and Cape Lookout and Cape Meares, basically. So, but the unknown thing was that as the geologic mapping was taking place through Oregon State University, when I was a graduate student there, under the auspices of Al Neen, they were able to start putting together the geology of Clatsop County, and they discovered, well, there's a chain of very tall, very steep, rugged mountains that runs northeasterly from here over to Napa. So we have Neocony Mountain, Onion Peak, Kidder's Butte, Sugarloaf, Saddle Mountain, and Wickiup Mountain, all the way to Nikolai Mountain. Each one of them is a lava pile. When you're at Nikolai Mountain, you're at the place where the lava is poured off the dry land and into the ocean. So they left behind sheets of lava going back towards the Longview area. But if you go down towards the southwest, instead of having sheets of lava with columnar joints like you normally see with gas bubbles in them, it's just shattered, glassy, fragmental rubble with pillows, which if you're familiar with lava, how it behaves when it goes into the ocean, hot lava hits cold water and it either explodes and shatters, or it gets chilled and forms this big gooey ball of lava surrounded by glass, which is what you get when you chill liquid rock, and it then pinches off like a big wad of toothpaste and rolls down slope and lands on the thing that preceded it, and it drapes one over the other like this, so you get a stack of rubbery pillows that harden up. And so if you go into certain places where the rivers have cut through this, you can see these stacks of pillow lavas. But mostly, they apparently came out so rapidly because when you're pumping 800 cubic miles of lava into the environment and some of it into the ocean in a period of a week or a month, you're really pushing a lot of lava into the ocean. So it just shatters, breaks up. And so if all these big rugged mountains are made of upwards of about 2,000 to 3,000 feet of glassy fragmental rubble that cements itself into one huge enormous mass and then is highly resistant to erosion, so that when the stuff finally comes out of the ocean, you've got this big hard mass of rock and surrounded by soft mudstone and soft sands that were on the seafloor at the time that they accumulated. And those wash away, leaving low hills followed by tall rugged mountains. They make very interesting habitat, by the way, with regard to the Land Conservancy. We're trying to buy some of the Onion Peak to Angora Peak area, about 3,500 acres or so. And it's unusual in that those big masses of glassy fragmental basalt, when they get cracked by faults, a lot of times break out to form the equivalent of large ice cubes, but they're stone cubes. And as they sit there in the rain and rot, they become rounded balls of fragmental rubble, and they form giant boulders, easily the size of this screen or larger. And they tend to slowly move down slopes. Sometimes they collapse as tall spires. And when they land on top of each other, you'll have one boulder here and another here, and the soils then creep away from underneath, and you get caves. So it's no wonder we have so many black bear up there. It's a caving mecca for black bears. There, everywhere you go, there's caves, and they're there, but those mountains have been tall and isolated geographically for about 10 million years. That's about the time the landscape rose out of the ocean. And so for 10 million years, we've had the equivalent of the Galapagos Islands just north of here, with isolated species that are evolving and creating new species. And so there are unusual plants and unusual insects, and who knows what we're going to find, but it's all part of a very unusual ecosystem stacked right next to the ocean. And it's got all the hallmarks of really exceptional land. It was eyeballed for national parks. When the state parks were first being put together by Sam Boardman, he looked at this and he said, "I've never seen anything better." He was able to get Oswald West State Park and Ecola Park, Hug Point, but ran out of steam, and the logging interests got into the high country and got their hands on it. The rest is history, but the intention is to try to acquire somewhere on the order of 10,000 acres up there and let it go back to nature. So we're in the process of doing that. It's a small commercial I work with. Anyway, if you're interested, check us out, nclctrust.org, and there's lots of stuff about it. One of the other things is that, to bear in mind, why would 3,000 feet of lava accumulate on the seafloor, preferentially at that particular location? It's that it was a trough, a low area, and it has its modern analog off of Astoria. The Columbia River cuts its own submarine canyon because dirty water comes out of the river. Being dirty and full of silt and sand, it's dense, and so when it goes into the ocean, it hugs the bottom of the ocean and goes shooting down the continental slope, and it cuts its own canyon. The modern canyon is about 6 to 10 miles wide, no, more like 6 miles wide, and about 3,000 to 4,000 feet deep, compared to the adjacent continental slope materials. If you look at these mountains going over northeasterly from here, they're roughly 3,000 feet high and 6 miles wide. It's the inverted Columbia River Canyon from the Miocene, upside down. And if you want to see the estuary of the Columbia River, go over to Hug Point. The Hug Point sandstones have driftwood in them that have teredos, which are shipworms, which are marine clams. There's also coal beds in the Angora Peak sandstone, which is from swamps that are fresh water. And there's even these interesting sandstones. They're cross-bedded sandstones. Usually sands form a bed, flat on top, flat on the bottom, stacked like this. But inside of these, there are these crossbeds that indicate that the currents were moving in one direction, transporting sand over the sandbar, and it builds out these foresets that are steeper than the top and the bottom. And then they turn and come back the other direction without any interference, no erosional event. And this is telling that the tide was going out and then coming back in. So out and in. And so you get these crossbeds going this way, then this way, then this way. We call them herringbone crossbeds, and they're an environmental indicator that you're in an estuary with tides going in and out. Further, the gravels that are in the sandstone contain quartzite and metamorphic rock fragments from northern British Columbia, or southern British Columbia, northern Washington, and northern Montana, but not down from Oregon. So it's telling us there are no metamorphic rocks really to speak of in Oregon, but there are in Washington and Idaho, so this has got to be the Columbia River. So here you are, right here. And the reason the Nehalem comes out where it does is that when it swung around as the Coast Range came out of the ocean, it couldn't penetrate through that wall of basalt. It was like a gigantic stone barrier. And so it just bumps up right against it and follows it right down here to where we are now. And that's why you have your estuary where it is. So in terms of the geology of the Manzanita area, you have Neahkahnie Mountain. Half of Neahkahnie Mountain is made of intrusive basalt, which is where the lavas, the rest of the story is the lavas, may have filled the submarine canyon, but they also went out through the walls of the canyon and penetrated the soft sediments and got between the layers and took off and went for miles. It gets a little hard to push lava out for miles, and so after a while it started filling them up, and so you get these lava reservoirs that are something like 1,000 to 2,000 feet thick, making these big slabs that we call sills. And from the sills, they snuck out and feathered their way out through the overlying sediments and re-erupted onto the seafloor in places. So if you want to go see the throat of a submarine volcano that's largely eroded away, go look at Haystack Rock at Cannon Beach. That's what it's made out of. In other places, there are sills like Castle Rock off of Arch Cape. That's just a part of a slab that got in between some sandstone of the Angora Peak sandstone. And Hug Point's a good place to see where these lavas were pushing their way through, folding the sandstones, which were still relatively soft and rubbery at the time that the lavas came out. And they literally blew it apart. And there are places just north of the final point at Hug Point where you can find just more shattered breccia, all this material that's been blown out and falls back into its hole and then gets cemented together until the ocean exposes it now. So that's the story of where you are. You have from here, basically from Neahkahnie Mountain down the slope to about Nehalem Road, you've got the older sedimentary rocks on which all of this was taking place, which over in Clatsop County we call the Smuggler's Cove Formation. You see it at Oswald West State Park. These are submarine undersea continental slope deposits where as the oceans fill with sediment and the rivers deliver sand to the sea, they build out these shoals, and then an earthquake shakes it and it liquefies, and you have liquefaction and it turns to quicksand, and it literally flows off the edge of the continent, down the continental slope, and goes out to the deep marine abyssal plain. It leaves these characteristic packages of gravel grading up into coarse sand, grading up into medium sand, into fine sand with ripples and rip-ups that it picks up along the way until it finally has seen the big slide go skittering by, and then it stops and dark clays and muds accumulate until the next great earthquake. So you find in the cliffs of Neoconi, or of north end of Short Sands Beach, these beautiful rhythmically banded sandstones and mudstones, each sandstone representing an undersea avalanche triggered by a big earthquake in the subduction zone. These things are making up the slopes from basically Neoconi Lake up towards your springs on the edge of the base of Neoconi Mountain. And these slopes are pretty stable, but they have slid down into Neoconi Lake where some faults have cut through. I would have shown you this because I just worked all this stuff up for the project up at Neoconi Mountain, up where they're putting in the subdivision around the water supply. So these slides, once in a while, will slide down, but for the most part, there are no houses in there. They don't pose a problem for most of us. There is a problem in that if you're on the west side of Highway 101, between the ocean and Highway 101, there is room for landslides on those slopes if you're north of Nehalem Road. It's all been mapped as landslide, and after having worked it up myself, looking at LiDAR and digging test pits for a lot of houses up there over the years, most of that terrain is made up of landslide rubble. Now, there's an unusual hill. It's where Nehalem Road meets the beach frontage road, and you can turn north and go around it. There's 2 or 3 city blocks of houses up on that sort of a lobate ridge there. That's an alluvial fan made up of blocks of basalt from Neoconi Mountain and sandstone from the Angora Peak sandstone, which is in fault contact with it up where the springs are. And you can trace this thing, it's sort of pear-shaped, and as you go up to the springs, there's a fault there that is probably where all this stuff came from. But the big question in my mind, given what I know about how steep slopes form and what alluvial fans do when they form out in the desert, it's a really steep hill for something made out of blocks of landslide rubble. So I think it's a block flow. It's a class of landslide. It's not a sloppy delta of silt coming down like in other places. This thing looks like it's a reactivated landslide that had once been resting up there where the springs are, and then decided to take off and come down. As near as I can tell, it's thousands or tens of thousands of years old and not likely to move again. But I think the hypothesis that I put forth to get a fight going with my friends in the business, you can get well, to tell the story a little differently, I was prospecting over near Mackay, Idaho, near the Snake River Plain, where the Bora Peak earthquake struck in 1983. I was there in 1982. And when the earthquake struck, it caused a lot of geysers to emit from the ground in places where it was just the slope, and it turns out alluvial fans. That what it says is that during shaking of an earthquake, you can compress aquifers and overpressure them, and they squirt up to the surface. So they're like geysers. And so for 5 or 6 hours after the earthquake, there were geysers coming up all over the valley. And I think maybe what happened up here at Neoconi Mountain is we had a subduction zone earthquake, which overpressured the fault zone that is underneath where the springs are, and pushed a lot of water out and liquefied these blocks of rubble that had fallen off the mountain earlier, and they scooted off down the hill and they came out and lost their water real fast and made this hill. And I think it's a cool story. It may not be true. That's the nature of geology. But I just thought I'd tell you because it's thought-provoking. Otherwise, the springs that are up there are all draining down to the south, coming down towards the low embayment there, where Nehalem Road runs through. They seem to have run up against the sand dunes farther to the south where the water tank is and where most of your homes are located. Those sand dunes, according to Kurt Peterson from Portland State, a classmate of mine from graduate school days, he says that most of the carbon dates that they've been able to get from soils and buried logs and shells indicate that the dunes are no more than about 5,000 years old. They have blown in various pulses though. And there's a younger pulse that came through on the western half of your neighborhood, running northeasterly, driven by the winter southwesterly winds that went up and through and then dumped some more sand in, kind of bulges out. And it's a relatively young dune. That's the one that likely will have problems with settlement or maybe slope instability out near its leading edge, because as these sand dunes have migrated up through the woods, they have pushed through the forest, and the sand advances down to the angle of repose, which, depending upon the conditions, is roughly around 60 to 80% slopes. If you're at 100%, you're probably at the extreme leading edge of steepness that the dunes can support. So an earthquake most likely would make a slope as steep as that to fail. But for the most part, from what I've been able to tell, living on a sand dune is a good thing. If your slopes are relatively gentle, you don't have a cut bank that's 10 feet tall, as steep as the sand can support, your house will probably do just about fine. Maybe a crack or two from lurching back and forth. But in terms of the ground stability, I think the dunes are all quite stable, with the exception of the north face looking down into that depression where the Halem Road passes through. It's a little wet down there. You've got the ponds down near the beach. The water table is shallow. The rule of thumb about whether or not you're going to have liquefaction that can lead to a loss of support because you've created essentially quicksand during the shaking, is that if the water table is 20 feet below the surface or more, you're not going to have a problem. The reason for that is that the overburden weight of the sand over that saturated sand down at depth will compress everything down. And if you've compressed it down, it can't shake and compress any further, because what makes liquefaction happen is the shaking of the earthquake will take particles that might be shaped like this wallet, and when they shake, they collapse, and they all fold up like this, and the water's got to go somewhere. So it seeks an exit, it overpressures, and there's a structural characteristic. If you overpressure something too much, you take away its internal shear strength, which means it becomes a fluid. So it behaves like water, which is what quicksand is. And if you have a shallow water table, say 3 to 6 feet under the ground, and you're built right there, you might have some problems with settlement of your house. I don't think the house goes glove, 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 and disappears underneath it all. Some places it does. Stuff like that can happen, but it's usually where you've put fill out over a marsh or a swamp. And the classic example is San Francisco Bay. My great-great-grandfather abandoned his boat on the banks of San Francisco Bay in 1851, and those boats all got buried under fill because no one would take care of them. And so they built the Mission District out over all of that. When the earthquake in 1906 happened, literally brick buildings went down 3 stories, and there were stories of people trying to find the right words. Basically, they rode a great big belch of air up through the muck and came out of the surface. I'm like, what the heck just happened to me? But there were a lot of people who are still down in those buildings and tombs. And there's another great story. This is a bad story, I suppose, but I like to use it just in case you're starting to fall asleep. In about roughly before 1700, which was the last time we had a big earthquake, in Jamaica, there was a subduction zone earthquake. I think it was in 1696. And at that time, Isle Royale had a big spit coming out into the bay from these very gentle coastal currents of the Caribbean. They don't have storm waves like we do, so the waves don't pound the sand down hard. You can't drive on their sand, you'd sink out of sight. Well, the British built their typical red brick buildings for trade and had a series of big red buildings on the spit. There were also some other nationalities that built canvas tents because it was hot and humid, but the British, they always dress in wool, no matter what the conditions are. And when this earthquake hit, the liquefaction took place, and the sand kind of glistened Now, this is from the royal proceedings of the Society of London. They wrote about it. They had woodblock prints showing this whole scenario. The earthquake shook. Everyone screamed and ran out of their houses and fell up to their chins in quicksand. And the ground shook for 4 minutes. When it stopped, the sand hardened around their bodies and they died. And they were left, and they show the people with the head sticking out of the sand. And then the dogs came through. That's the rest of the story. I won't go into detail. I'm going to fill in the rest. Until there was another earthquake in, I think, the 1930s or 40s, a lot of those buildings had just gone down like an elevator. The sand had sort of bulged out to the side. And so divers used to go down and explore these brick buildings. They were still standing under the ocean until there was this more recent earthquake. And then they fell apart. But you can still find the brick remains down there. So back to the story. Let's see, what is the story? We do have mostly young wind-blown sand here in the Manzanita area. The slopes in general are gentle enough that they're not going to liquefy and flow. They might stretch a little bit. If you have a house on a pad that's been cut into the dune, you can take that sand and put it over here, and provided you compact it properly, it's not going to sag and your house will be fine. If you just have a bulldozer, shove it out and drive on it a little bit, it'll sag over time because that sand is going to continue to settle, and your house will snap across the fulcrum where it goes from cut to fill. And at a few places, but not too many in Manzanita, to solve that problem. The only time I've ever had a problem going into retrofit something in Manzanita, it's been where people built on a bank too steep and put in a retaining wall too limited, and the wall moves so the house goes with it as it fails. So if you happen to be on an overlook, you might be at risk of losing some support during the shaking of an earthquake, and it might cause damage to your house. Maybe you're already experiencing damage to your house. That's a good sign that you'll have further damage during the shaking of the earthquake. Liquefaction is one thing. Shaking amplification of the ground is another, and that's usually worse if you go thicker and thicker young alluvial deposits. And since most of Manzanita is entirely on that kind of stuff, I would expect your shaking amplification to be increased by about 20 to 30%. What does that mean? It just means that if you build a new house nowadays, we'll tell you to increase the resistance so they'll put more shear walls in the building. If you've got an old house that's resting on concrete footings, you might find that your house is going to groan and creak during the shaking of the earthquake. And so you'll end up with these cracks opening up around the frames of the windows or around the frames of the doors. And it'll be a sheetrock repair project for you. Maybe broken windows if you have wood frame windows that try to go into parallelograms. Those could crack and break. But the homes in general probably won't fall apart. Wood frame homes do pretty well in these big subduction zone earthquakes. So I could talk a little about what we know about the earthquake. I think probably most of you know what to expect from the sounds of it. Is it necessary to do that? Would you like to know the history, the probabilities, or the statistics? I could throw stuff out for you.
Yeah.
Okay.
We'll hear everything.
All right.
But before you do that, can I just go back to the picture? So the area that we're living in, the Highlander area, kind of up the hill, basically what you're saying is that is a big sand dune.
Yeah.
Okay.
Yep. Everything from here all the way to the top of the hill before it drops down into that depression.
Right.
It's all sand dunes.
Right.
And the sand dunes are about 100 feet thick, maybe less in places. We don't know for what the hill shapes were that are buried under there.
Right.
Could be 20 feet thick, could be 100 feet. I do know that when I look at the sands on the western side where that there's a few ridges along that run northeasterly through the neighborhood that represent the flanks of a migrating dune as it went on by, kind of left some wake as it went. Those sands tend to be a little looser, a little more prone in need of compaction because they're younger. But if you get out on the east side of those little fringe effects, you can tell when you're in older sand dunes because the insect burrows don't collapse. And when you see a road cut, you'll see this much sand sticking out. It's full of bee holes, worm holes, beetle holes, and it's kind of brownish and kind of mossy looking. And it's because so much stuff has rained down through the sands that the sands have been cemented somewhat with humic acid, iron oxides, maybe even a little bit of aluminum oxides get in there and hold it together. And so if it were a young dune, poor little bud goes in there and gets smothered by the collapsing sand. So you can just look at the wormholes and say, old dune, strong sand, build here. It's that easy. I hate giving away professional secrets. It ain't rocket science, folks.
So old dunes, old stable dune.
Old stable dune, yeah.
Old stable.
Yeah.
Yeah.
The only problem is one that you create by pushing sand out and trying to make it too steep and too wide. And a lot of people do that to make their homes have level lots for the construction. But so if you have had a poor job of compaction, you may have problems in the earthquake. If you took care during construction and compacted that sand, it'll be pretty strong. It can get as strong as almost as concrete under compression. So it's not going to go anywhere, and your chimney won't disappear like an elevator going into the ground. It only happens if there's some place for the sand underground to go, and that requires flowage. And if it's dry, it won't be able to flow. If it's wet, it will be able to flow. But up on these dunes, the water table is probably 50 feet below your house. So you're so high up, you're in the dry, stable stuff. And you're in great shape.
If the water tanks were.
Oh, that's a it's possible water saturation from water might do something.
And the second thing, in the 1700 earthquake, could you tell what the effect was in this area?
There aren't strong indicators that tell us anything. The only thing we know is where the tsunamis have come in.
What's the question? What is the
I
question?
couldn't hear the question.
The question was, are there any physical indicators of the 1700 earthquake? Like landslides, we don't, there are landslides all over the place. We haven't carbon dated the trees that are buried in the landslides, which I think is a good idea. I've often suggested to the state of Oregon that they have a slush fund for these kind of questions. When you find something like a tree buried in a swamp, carbon date it, put that in a database and build the database through time, and pretty soon you might see that the earthquakes all happen at the same time, triggered by earthquakes. But they can be triggered by lots of other things too, so it's really hard to say. Kurt Peterson, who talked about the sand dunes, also has done research on archaeology of the wax Spanish galleons that wrecked here. One wrecked just before the 1700 earthquake and tsunami, and another one wrecked just after it, apparently. And my predecessor, Paul C., who is from a pioneer family on Clatsop Plains, recalls his uncle around 1910 to 1920 taking a buckboard over Neocony Mountain from Seaside to get teak lumber out of the dunes down here, down by the state park. And it was from one of the galleons. They were made out of teak, and they apparently had been picked up by the tsunami at roughly sea level and moved up to about 35 feet above the dunes, or above into the dunes. But the dunes are different in those days. There was a lot of blow through. We didn't have European beach grass, and it didn't trap and build tall dunes. It was a sheet that just blew on through and kept going. So it was easy for a galleon to be left high and dry and never be buried. And we looked for it. I think we got within probably a city block of where those things are. It's got forest on it now, and I'm not sure we'll ever see them again. But magnetometers and cannons and all these other things that go on, it's possible with diligence we might relocate those. It's food for thought. Anyway, so with regard to the earthquake history, I like to quote Chris Goldfinger, also an old roommate or office classmate of mine. We're all from OSU. We have to control everything. And so Chris has been, got his doctorate, I think, in '94 or something like that. And he's been doing offshore earthquake studies ever since. And he's a marine geologist, and one with a very strong structural background, which means he specializes in earthquakes. So to figure out whether or not we've had earthquakes is to look at these turbidite deposits that I was describing locked up in the Smuggler's Cove Formation. They're forming now off the coast, and they're triggered by earthquakes. To find out whether they're a particular turbidite that you core offshore in 9,000 feet of water is from an earthquake, you basically core all the way up to Vancouver Island and down to Cape Mendocino, and you look to see if you can find similar cores and compare them. Usually there's a pretty good indicator in the layering. Somewhere down here, about 7,700 years ago, you'll find the volcanic ash of Mount Mazamas, penultimate eruption. Big white ash layer. It's very distinctive. It's got crystals in it that are diagnostic of Mount Mazama. So there's always about 8 earthquakes or turbidites above it. That's 7,700 years ago. I've got to get these numbers right. 13. There's 13 turbidites above it because they happen on average about every 500 years. Goldfinger likes to say there is no better known fault zone in the world than Cascadia now. For one that we kind of realized was active only a few years ago, we now have a more dense and thorough, comprehensive database of it because Oregon State University has been doing oceanography off the coast since the 60s. They didn't know what it all meant, but they didn't throw their cores away. We knew that there were turbidites in there. We just didn't know if they were triggered by earthquakes. The day was, when I was an undergraduate, you'd ask a professor, say, it's a subduction zone, right? Why no earthquakes? They go, tut tut. It's child, it's this subduction zone is warm because we have a spreading center less than 200 miles offshore. So the seafloor is warm when it gets here, so it behaves in a plastic ductile manner so it doesn't have earthquakes. Well, that's wrong. It just has a habit of waiting quietly without pinging or making any noises until it has itself a big magnitude 9 earthquake. These earthquakes don't usually give themselves advance warning. You know, the one that hit in Japan did have a precursor, but it was just like 50 other earthquakes that randomly happened there. It's hard to say what's a precursor and what's not. There's another thing. Back in the year 2000, we had a meeting in Seaside, a Penrose conference. These are the most prestigious of all geologic conferences put on by the Geological Society of America. Penrose put up the money for these things. That's why he gets his name on it. And we dealt with the 1700 earthquake and its 300th anniversary. So we held this meeting in Seaside, and I got to attend because I was the gopher. And I helped set things up, and so they let me hang out. And one of the things I met was on a poster session, a guy getting his doctorate from British Columbia. Can't remember the university. It's not UBC, but one of those in the Vancouver area. He had gone out to a marsh west of Victoria, cored down through the 1700 tsunami sand layer. Basically, what he encountered was a core in this thick. The bottom 1.5 was estuarine peat deposits, and then there was a sand layer from the tsunami that was washed in over the grassy environment of the marsh, and it turned into a mud flat, which says basically that the land dropped several feet, killed all the grasses and trees that could potentially grow there, and left a place for mud to accumulate. And so mud accumulated, then it started getting rooted, then it started getting kind of peaty and turned back into peat. Now it's peat again. So this change in between the earthquake, the tsunami coming in, having peat at the bottom and mud on top, indicates co-seismic subsidence. And so he was looking at the palynology, the pollen deposits in the strata of this core. And he noticed underneath the turbidite or the tsunami sand layer, about this far down, some of the plants started to proliferate that thrived up above. It meant that the land was sagging down before the earthquake struck, and it warped down maybe a few inches, enough for a few years before the earthquake struck. It was an indicator of this. His name is Jonathan Hughes. So I got his thesis. Lo and behold, his thesis doesn't talk about this. I think he decided there was something not quite right here, so it never got into his thesis. And it's one of these weird things. But notwithstanding all that, it's still a fact that you can see sometimes the land may give it up. It's presently coiling up with energy. We're all deflecting to the northeast. We move about an inch a year that way, and we're rising a little bit. When the earthquake hits, we'll be warned that it'll let go and we'll all relax and go back the other direction and drop. So here's the statistics. There have been 21 earthquakes in the last 10,000 years. Of those 21 earthquakes, 6 occurred within 300 years. Now, we're at 318 years. So 6 would have occurred before ours will strike. The next 300 to 350 years, all the others will strike except for 4. The weird 4 are what we regard as the long time period between clusters of earthquakes. So there are 4 or 5 clusters starting 10,000 years ago up to the present. And the cluster that we're in right now has a chance of 1 more earthquake, and the odds are about 80% that we're still in the cluster, and it's been averaging 330 years between earthquakes. So we're at 318 years, it's 330. So if you can't afford to be wrong, you have to do things to prepare for this. And so the earthquake will strike without warning, most likely. It will shake for 3 to 5 minutes. It will be followed by a tsunami that will reach shore at about 20 minutes, and the crest of the tsunami will reach shore in 35 minutes. I do know from Kurt Peterson's work, where he looks at how far did the sands get dragged inland for various places along the subduction zone and comparing to Japan in 2011, that of the last 6 earthquakes, 3 were around 25 feet high and 3 were around 55 feet high.
55?
Yeah, at the beach. And then now the state models them. They have them even bigger because they can create scenarios with the way the flexures and the crust work that they can lift the ocean and make a much larger wave. But the big question is, what do you want to plan for? Do you want to plan for the worst possible model scenario, or do you want to plan for the worst observed in the last 3,000 years? And that's kind of a condition that each community has to choose for themselves.
So the 55 foot, in terms of the Lugano charge, is there some kind of comparability?
Well, there's small, medium, large.
Right.
It's right around large, middle
Right
of
around
large.
large.
Yeah.
So,
Are you saying that we're unlikely to see a moderate earthquake, that it will build until, and we'll just see like a 9.0?
I would plan for the worst shaking, but don't plan for the worst tsunami. The unspoken thing is that the model that the state uses is not supported by Kurt's work. And what it says is that small subsidence may not necessarily mean small shaking. It may make a certain size turbidite off the coast, which is what they use to say how big the quakes are. But there's no correlation that how far in the tsunamis go or how high they were to the offshore work or anything else. It turns out it's far more complicated than the modeling assumes. There's scenarios about how stress and strain works and how coiling energy works, how it's given up, and it's just really a complicated mess. So you can go with models, or you can go with real-time observations. You know what's really happening. But nothing says. Kurt's work says it's only for the last 6 quakes. What about the last 16 quakes? There might have been a bigger one or 2. We don't know. It's just not recorded because the estuaries are only 4,000 years old. That's where we get our information.
so the small quakes that have occurred recently off the coast, the Oregon coast, they're not an indicator of anything.
No. Those are just the edge of the plate grazing against stuff farther to the south or farther to the north. And they've been going on forever. These are no surprise. But everything between them, from Cape Mendocino up, or maybe Cape Blanco, I should say, up to the north, it's all locked up. And that's waiting to break, and it's not giving us any indication when it's going to happen. The area from Cape Blanco south, Coos Bay to Brookings and on down, is on a microplate. It's called the Gorda microplate, and it's being crushed from the south to the north by the San Andreas trying to propagate up to the north. And so there's a whole lot of mostly strike-slip faults in that area. It has twice as many earthquakes down there, big ones, as we do up here, according to Goldfinger's work. So they have earthquakes on average every 245 years, and now it's been 318 years. So they're ready to have one, and it'll pop off in the next 5 to 40 years probably. So I like to scare people and say it's going to hit in 5 years, so it'll make them take this a little more seriously.
But it could
Anyway.
hit
I
tomorrow.
like your attitude.
It could hit tomorrow,
It's,
right?
it's
It
all,
could.
it's all about preparedness, and one of the things, just in terms of what Thomas said, in any of the evacuation maps that you